In this set of notes, or this video, I guess I should say, we're going to take a vector in Rn, and we're going to define something called the norm of a vector. And the notation for the norm is like two absolute value signs sitting next to each other. Our geometric intuition is that the norm represents the length of a vector. And we'll now state the actual definition that the norm of a vector is the square root of the dot product of the vector with itself. So, two remarks. We said that even though, according to the definition, U transpose times U, the dot product should give a 1-by-1 matrix, it's not convenient to think of it that way. And here's a good application as to why it's not convenient. You cannot take the square root of a matrix. Secondly, we said that the dot product of a vector with itself is always non-negative. Now you can see an application of that. That fact ensures that this square root is a real number. We've said that norms represent lengths. Let's demonstrate this in R2. So let's say we have the vector 3, 1. And we're visually representing that as an arrow connecting the origin to the point 3, 1. So if we create a right triangle like this, one of its sides is length 1, the other is length 3, and this hypotenuse is the length of the vector. So we can simply apply the Pythagorean theorem here. The norm of U squared is 1 squared plus 3 squared. The norm of U is the square root of 1 squared plus 3 squared. And what's U dot U in this case? Well, here's U. Here's U again. To do the dot product, we multiply component-wise and then add. So we get 3 squared and 1 squared. And to get u dot to u, we add them together. So the length of this vector, according to the Pythagorean theorem, really is the square root of the dot product of the vector with itself.